Sorry. After a series of highly insightful sessions over the past few days, we continue this academic journey today with renewed enthusiasm. We are privileged to host two more distinguished experts in the field of civil engineering. First is Dr. Chandan Pradhan sir uh, from Department of Water Resource and Ocean Engineering, National Institute of Technology, Karnataka. And after that, Dr. Pratik Gupta, Associate Professor, Department of Civil Engineering at Indian Institute of Technology, Delhi. We are honored to welcome Dr. Chandan Pradhan sir, currently serving as an assistant professor in the Department of Water Resource and Ocean Engineering at National Institute of Technology, Karnataka, Surathkal. Dr. Pradhan hold a PhD in civil engineering from IIT Guwahati, where his research focused on process form relationship in a continuum of Pratt channel pattern. He also hold a MTech in water resource engineering from IIT Guwahati. He further pursued a postdoctoral fellowship focusing on the design of smart flood wetland monitoring system and assessment of biomorphological health in the flow system through underwater exploration. His research expertise lies on fluvial geomorphology, river health and recovery, remote sensing applications, hydrographic modeling, and stream health management, with the special emphasis of Himalaya and Peninsular river system. He has made significant scholarly contribution, having published in the reputed international journal such as Katina Scientific Report and Geomorphology and the Journal of Hydrology. His work highlighted geomorphic indicators, effective discharge, river recovery frameworks, and morphodynamic modeling. Dr. Pradhan is also co-PI in a prestigious national level project like Krishna River Basin Assessment and under the Ministry of Jal Shakti, Government of India. He has convened and co-convened session at major international conference. As a passionate academic, Dr. Pradhan sir has delivered expert lecture, master classes, and hand-on training session on GEE waste hydrological modeling, river restoration, and advanced hydrogeomorph survey at a leading institutions. He actively contribute as a reviewer for renowned journal and is a member of several national and international professional bodies, including American Geophysical Union, European Geoscience Union, International Association for Hydro Environment Engineering and Research, and the Indian Society for Hydraulics. We are excited to gain insight from his vast academic and research experience in today's expert session. Welcome you, sir.
Thank you, Dr. Anuj, for this introduction.
Thank you, sir.
So, shall I go to my presentation? The screen is visible.
Yes, sir. Yeah, visual, sir.
Just putting full screen. Screen is visible.
Right, sir. Visual, sir.
So, good afternoon to everyone. I'm Dr. Chandan, currently working as the assistant professor in Department of Water Resource and Ocean Engineering. Prior to this, I did my tech PhD at IIT Guwahati in Department of Civil Engineering. After that, I was briefly working with on the Himalayan River Basin for a smart flood monitoring project during my postdoctoral fellow. And all my expertise is mostly so far on the river recovery, river health monitoring, morphodynamic modeling, and process-based understanding of this our Indian Himalayan and Peninsular river system. So I have been very grateful and got the opportunity to take PhD and also during currently in working as assistant professor at NIT Surathkal and very close to the Western Ghat River system. So I've been part of many field visits for the last 10 years, including Brahmaputra, Brahmani, and currently also I'm part of a national mission project on Jal Shakti for the Krishna River vessel. So also I'm going on the field to the our Western Ghat River, which is very dynamic and very, let's say, beautiful in nature, and their process form understanding is very much complex. So coming to this today's session, mostly I'll highlight on what is our river recovery concept, how it has been started by the Australian and European group of researchers, how we can implement it to our Indian river system, and what are the current advances in river basin management study in the line of river field visits. So I'll start with how this came into the picture of river recovery. So far our knowledge on river health is mostly dealing with what is your river water quality. So water quality, we have certain standardized parameters. So we take into account there are certain ranges are there above that threshold limit. If any two or three parameters changes, then we have an idea about what is the biological degradation is happening or physical changes that is happening. So that we associate with our river health. So currently after 1990, what it started in mostly in Australian group of researcher and European group of researchers that there is a concept of river recovery. So river recovery means we are giving any kind of disturbance to the river system. After the disturbance of the river system, whether river is coming back to a natural state, whether the river is developing another kind of altered condition, and how it is affecting the morphology as well as the biological property as well as the ecological enhancement of the river system. So this came into the picture of the late 90s and it was first implemented by Australian group of researchers. Then uh, in our Indian river system, the river recovery knowledge is very limited. So far, we have not gone detailed study, mostly on the basis of morphology and how the morphology is understanding interacting with our process and form. So if you go to our Indian river system, the rivers are very dynamic in nature. If you go to the Brahmaputra river system, so the Brahmaputra river system is highly dynamic in nature. It can have very high bank erosion. It can have very large amount of debris load in terms of large tree trunks can come and they can deposit during the floodplain. The bank of the river can be composite in nature. Okay, so in case if you go to the tributaries of the Brahmaputra, which are also very large in nature and also dynamic, some tributaries will form a gravel bed, some tributaries will form the alluvial bed. In addition to that, we have the anthropogenic disturbances in terms of the dams, weirs, and barrages. So there is a very complex process form understanding that is happening inside the river system. Now, if you come to our peninsular river system, so the peninsular rivers are mostly stable. Okay, the bank of the peninsular rivers are very much stable, and we can see the most of the dynamic properties of the morphological part of this Indian peninsular river system is happening inside the river. So sometimes the in-stream vegetation can be enhanced. The in-stream vegetation interacts with the morphology of the river, and during the flood, that plays a significant role in controlling and behaving how much flood dissipation will happen between the in-stream vegetation as well as during the floodplain. Also, we have the wetlands are there. How much wetlands are contributing to the flood peak reduction during the peak extreme event? So that was very high dynamic things that is happening inside the river. So that in addition to the our Indian river system, we have the very large amount of dams, weirs, and barrages are there. When you build any kind of dams, weirs, and barrages, there are three cascading effect happens. First one is the change in your flow hydrology and the sediment part. Second, changes that can happen during the morphology, and we call the third impact, that is third order impact, that is on the ecology part. So whenever we are disturbing the river, so there will be a cascading process, or it can happen at a simultaneous one. That will be the interaction between your flow hydrology, morphology, and the ecology. So our river systems are very large in nature. So whenever we are giving any kind of disturbance to the river, the disturbance propagate both in the upstream direction as well in the downstream direction. So currently we are only quantifying what are the changes that is happening. So in order to understand the process behind the changes, we need a very detailed, thorough understanding of what is the river resilience are there, what the river recovery potential is there, how the different components of the rivers are interacting with each other, how the significant climate change impact is there as well as the anthropogenic impact is there. So from that we have a different concept of like 12 concept of river recovery or the geomorphology things are there, such as river recovery, river connectivity, river sensitivity, what is the channel forming discharge at the upstream end, what is the channel forming discharge at the downstream end. So we have a very complex process from understanding and the interaction that is happening for both our Indian and Peninsular river. As well as when we give any kind of disturbance to the river system, the first thing that happens inside the river is there starts a relaxation time period. For example, if my river is, we are building a dam in 1980, so maybe after 30-40 years the river will adjust to the changes and the disturbance will not be that happen. But after 30 years maybe the disturbance will starts to propagate and the river may change its morphological pattern, may change its ecological behavior. So whenever we are discussing with any kind of river system, that we have to be very careful how the river dynamic is there, how the flow, sediment, morphology, ecology both are interacting each other, and what is the additional climate change impacts or the anthropogenic impacts that is prevailing inside the river system. So to understand this thing, we took the first study area, that is the study area 1 in Odisha. That is one large river system is there. That is your Brahmani river system. So whenever the Brahmani river system, in case of the Brahmani, it is a large river having a catchment area of more than 39,000 kilometers square. There is a large dam, that is your Rengali Dam. In 1985, it was constructed. So gradually, we have seen that during our field visit, the river is slowly a braid formation or the sandbar formation inside the river is happening, and the sandbar formation is very rapidly increasing in recent years in the downstream end. So we thought of that how to integrate the channel forming discharge to this kind of river system where we can quantify that which discharge is responsible for this braid bar initiation and which discharge is responsible for the changes in the in-stream behavior property. At the few locations we have seen that inside the river there will be the mid channel bar, and the mid channel bar we have the vegetation part. So there is an indirect indication that the vegetation is gradually stabilizing inside the river system. And we thought of proposing one equation such that we can quantify in future how much change in your breeding behavior will be there. So we term that equation as your probability of breeding equation, and we develop a concept of threshold energy such that whenever the river is exceeding any kind of threshold part, the extra amount of energy what the river has that can be dissipated forming any kind of sandbars or morphological dynamics. So with the help of geospatial technology through remote sensing, we analyze the landsat data. We have a long-term flow sediment data along with a very thorough field vegetation. We indicated one study area and we applied that mathematical equation, and we found out that whenever the river is exceeding any kind of threshold energy, the river is dissipating that extra energy in terms of forming morphological units, geomorphic units such as sandbars. And if the sandbar is gradually stabilizing, then in-stream vegetation is coming to the picture. So the whole idea behind this study was that to find out which one is the channel forming discharge. So in very simple term, when we talk about the channel forming discharge for any kind of river system, we take that there are three types of channel forming discharge are there. One is our bankful discharge. That means my flow at the bank to bank at during the very high peak floods that controls my channel. Also, we in traditional knowledge we have that effective discharge. That effective discharge is discharge which carries long-term sediment load in long term. So maybe that discharge is responsible for the channel behavior. Also, another some researcher we have linked with a return period of 1.5 year as our channel forming discharge. So through this study, we propose that in case of peninsular river, which are behaving very microchannel in nature or channel in channel physiography or compound forms is there can be multi-channel forming discharge. So one channel forming discharge can maintain my high back microchannel back. One small channel forming discharge can maintain our the smaller channel or the inside channel, and in between that the extra amount of energy what is exceeding our threshold can be dissipated forming our sandbars or any kind of morphology pattern. So this was the whole idea behind the initiation of river recovery work. So then we proceed to the understanding of how we can integrate any kind of vegetation landforms into this kind of equation. So whenever we discuss about this river recovery, as I was telling, this was started from the Australian river, that is our Bega catchment. So whenever we are giving any kind of disturbance to the river system, whether it can go to a degraded condition or it can itself create one new kind of created condition. So also we have different kind of river recovery model as per Phillips, that if you consider a river as a spring system, the river may behave a linear way. Sudden propagation of the river morphodynamic changes will be there, or the river may oscillate between two endpoints. Sometimes multi disturbances can form one kind of convergent recovery model inside a river. Sometimes many disturbances can we have one single endpoint and it will be divergent in nature. Or sometimes in the mostly in the Himalayan river system, the river system which are very dynamic in nature, there will be a connected disturbance theory, so that multi-parameter changes will happen and a one process will have a many kind of response variable. So this will be very complex in nature. So in case of our peninsular river, again we saw that if you take one cross section of our river, the rivers are mostly microchannel form. Here the floodplain vegetation, large tree trunks are there. In case of in-channel physiography, we can see our sometimes shoot channel cutoff will be there, mid-channel bar formation will be there. On the bar, sometimes the extreme vegetation stabilization will be there. Close to our bank, the bench formation will happen. So different zone of floodplain, different zone of interaction between your flow, sediment, morphology, and ecology are there, and different type of channel forming distance can be formed depending upon which zone we are interacting. So we have different inundation depth, different duration frequency analysis there, different rainfall contribution, different groundwater moisture levels are there. So this is a very complex in nature, and then this can be taken as one randomly interconnected kind of river recovery model. So then we proceed for our study area selection. We selected Mahanadi River, one stage of the Mahanadi just downstream of Hirakud Dam. The Hirakud Dam is very large dam which controls significantly the flow, sediment, morphology as well as the ecology of this Mahanadi River. So we did our extensive field visits, mostly in the pre-monsoon and the post-monsoon, and we saw that the river stretches or the study area is gradually stabilizing through the linear bench formation. Bench is nothing but inside the river if the vegetation colonization is happening. So this here the vegetation colonization is mostly on the linear bench. Sometimes close to the low flow channel, we have the lateral bar, and these lateral bars are colonizing through these six type of vegetation patches. So these six type of vegetation, which have different plant form, different planting time, spreading potential, as well as the height, they are indirectly controlling the morphology as well as the flood inundation behavior of inside the river system. So we thought of how to integrate this kind of in-stream vegetation theory, in-stream vegetation landform into our river recovery model. And to propose a river recovery model, we took the help of two indices. One is our in-stream vegetation through NDVI classification in Google Earth Engine environment. Through long-term spatio-temporal analysis, we took from 1980 to 2020. We calculate what is the in-stream vegetations are there inside my channel through NDVI. Also, we took at the gauging location what is the change in the hydraulic property or the hydraulic geometry that is happening. So we developed one entropy indicator that we term as cross-sectional entropy indicator.
Sorry, mistakenly muted. Sir, please unmute. Actually, oh,
Now it is okay.
yes, sir.
Okay. So we integrated both this Google Earth Engine based cloud computing of vegetation and the cross-sectional entropy. Both we indicated and form one river recovery indicator that we term as normalized river recovery. And we link this normalized river recovery with our process-based, whatever the first study area we have received, that is in the Brahmani, the process-based indicator formed through our channel forming discharge. So we took the help of Survey of India topography to analyze what the bank's behavior is there. We saw that during last 50 to 60 years, the microchannel bank is very stable in nature. But inside the channel, the river slowly the vegetated landform. This is the vegetated landform. They are growing in nature. So we thought of taking two contrasting study area. the tributaries of the Mahanadi. Both are controlled by your regulated flow. And we saw that where is the high density of the plant biomass is there. In both the cases, one case in the plant biomass is very close to the bank. In one case, the plant biomass density is more inside the instant channel. Okay. So, but in both the cases, we have seen that from 1985 to 2020, the in-stream vegetation patches is increasing. So we develop one indicator, that is the normalized river recovery indicator NRI, and we link with our vegetation percentage and the change in the entropy value. So we saw that in case of the river where the plant biomass is very much significantly dominating over the entropy part of the change in the channel cross section, in that case the river has a very strong recovery potential. So in direct way we can say that up to a certain percentage of vegetation inside the river system can help stabilizing my lateral bars or longitudinal bars or the morphological behavior, and they help stabilizing the river system, and the river recovery potential of the river can be increased. So we thought of linking with one conceptual diagram between two endpoints because we are discussing on the river recovery model. So here our two endpoints will be one that will our fluvial disturbance, that is my FD. Another endpoint can be our self-organization of the vegetated landform. Let's say that is SO. So self-organization of the vegetated landform, if it is dominating over the fluvial disturbances in terms of the flood, then means there will be a high chance of the river recovery potential inside the river system, and the river can maintain a very good health or the river recovery health. But where the repetitive fluvial disturbances cannot dominates over the self-organization of the vegetated landform, in that case the morphological dynamic will be very much active in nature, and the river recovery potential may decrease in such river system. So far I was discussing how to form channel forming discharge and the river recovery for smaller river system that is weakly braided form. But how to integrate this theory for a large braided river system which is very dynamic in nature? That is the Brahmaputra river. So if you compare any kind of peninsular river with our Brahmaputra river system, we can say that the Brahmaputra is very highly braided in nature, whereas our peninsular rivers can be moderately compound, microchannel form, and weakly braided. The banks of the river can be unstable because Brahmaputra is prone to very much high bank erosion, but in case of the peninsular river, it is mostly stable. The peak discharge in the Brahmaputra can exceed 50,000 meter cube per second. Also, the sediment load can be in terms of 400 million ton per year. So we are dealing with a river system which has very much high sediment load, bank erosion potential, the discharge variability, as well as the morphology. If you see all kind of geomorphic units starting from the mid-channel bar to longitudinal bar, and the island formations are there. These islands are much more stable inside the nature, and they also contribute to the morphodynamics of the Brahmaputra river system. So how to develop a recovery model and how to categorize the any kind of resilience based morphological or management strategy for such highly dynamic in nature. So we thought of taking the help of Google Earth Engine cloud computing. So with the JRC surface water data, we find out the post-monsoon median low flow images. So from this low flow images, we find out what are the dominant geomorphic units are there. From the dominant geomorphic unit, we thought of developing one indicator, that is our locational probability index. So I'll not go much detail into this locational probability. That means that I'll assign one probability value to each river pixel inside the river, and what are the chances of getting the low flow channel at the particular location. So indirectly, this locational probability index will tell me what is the river recovery or the resilience of the river system. Then we linked this LPI or the locational probability index to any kind of process-based indicator, whether it can be a channel forming discharge in terms of the bankful discharge, effective discharge, or a discharge with certain return period. So for the last 35 years of Google Earth Engine data, we classify the river into different zones. One zone can be nodal point where the river width is very much smaller. Similarly, it can propagate from the moderately braided to highly braided, and we can see the river has very dynamic low flow channel as well as the sandbar dynamics are there, and they are complexly interacting with each other to form a very much highly braided nature. So we thought of linking this with this spring theory such that uh, in a highly graded form, the river may have two thresholds. So one threshold will operate at a low flow end, another threshold will operate at the high flow end, and the river will oscillate between one end of the threshold to the another end threshold. Here, the primary channel will be linked with the secondary channel. Secondary channel will be linked with the third order channel. So, and all three are connected with the spring theory. So, whenever one disturbances to the primary channel is happening, it will propagate to the tertiary channel. And whenever any disturbance to the third order channel, that may also propagate back to the primary channel. So this we published in Catena Journal, and we thought of developing one resilience-based management strategy based on what is my LPI, that is a locational probability index, what is the threshold, bank erosion potential, and what could be the balance between the nature-based solution to the engineering-based solution. So we thought of developing this resilience-based management strategy. So it was finally published in Catena. So our whole idea behind this channel form and discharge river recovery that the river can behave as a spring, may oscillate between one channel to the other channel, and whenever it is exceeding another threshold, that excess energy can be dissipated, forming any kind of geomorphic unit. Sometimes the geomorphic unit can, the excess energy can be dissipated by the vegetated landform with a certain percentage of covering the extreme area. And in case of the highly graded threshold, maybe threshold will have multiple parameters, and in between the threshold, the excess energy are dissipated. So this all study was conducted through the combination of Google Earth Engine, cloud-based computing, as well as the numerical modeling, and mostly through the field investigation of the geomorphic units. So my point to highlight is that whenever we talk about our any kind of morphology or the fluvial morphology study, the field investigation is very much important in nature, because in one project we are thought of developing the national waterway. So we went for the field visit, and we have seen that in the British time period, one where a barrage was constructed, and at this location the river is mostly stable in nature. So such kind of field photographs is very much also helpful for how we can validate our numerical model. So we also did many kind of field visit to the Brahmaputra river. In case of the Brahmaputra river, we have seen that the mid-channel bars are very much large in nature. Inside the mid-channel bar, the island forms are there. Sometime on the inside the river, the mid-channel bar, the nutrient content after the flood will be very high, and these are subjected to the agricultural part. So currently, we can say that socio-economic condition of the nearby locations is also depending upon river, and they are also depending upon your agricultural livelihood inside the river system. So this is one part of river understanding through field investigation. Also, there is recent advancements of artificial intelligence and machine learning that can also help to understand our river system. That recently I was talking about this locational probability index, how it was developed through this Google Earth Engine cloud-based data of the JRC data. So in case of the Google Earth Engine, we can see that what is the channel forming discharge are there and how they are changed to the water occurrence through any kind of disturbances. So currently in the Himalayan and Peninsular river system, we have many kind of engineering solution as the nature-based solution. So we need a very detailed understanding to understand our river. Also, currently I'm part of this Ministry of Jal Shakti Krishna Basin project. So in that case also we have a very much strong importance or the influence of socio-hydrology. So currently we are conducting many kind of human river interaction study and how the humans is dependent upon the river system, and how we can develop such a resilience based or recovery based management strategy so that it can be helpful for the ideal local community, and that can prevent any kind of risk such as flooding or any kind of disturbance between the human and river. So for that, we have conducted doing many kind of field visit with river survey equipment. Currently, we are doing with this ADCP, that is the acoustic Doppler current profiler. Another is our echo sounder. This ADCP and echo sounder both give bathymetry data as well as the three-dimensional the velocity profile. From the three-dimensional velocity profile, we can link with one empirical equation of suspended sediment data generation. Also, during our postdoc study, we have worked with the underwater rovers, that is ROV. This ROV can be placed and it can go inside the river, and they can capture any kind of ecological behavior inside the river system. So we have fitting many kind of camera and sensor. Through this camera and sensor, we'll occupy what the river pictures are there, and we'll analyze or post process that image later on. So this was our ADCP survey in the Brahmani we did during very high peak flood, and we took many cross-section transit for our national waterway project. Also, I want to understand like our rivers are very much dynamic in nature. So whenever we are understanding the river, one multifaceted approach is required. So that approach can be one part of remote sensing, one part of numerical modeling, one part of physical modeling also. But in recent days, we have to also implement the field-based investigation, and because there is a complex understanding between flow, sediment, morphology, and ecology for our large river system. So so students can go through this. Many websites are there. So this kind of website can be helpful for understanding river recovery. One website is our JRC Global Surface Water Episode. So here they can see what are the water change intensities there, for water seasonality is there, annual water occurrence is there for the 40 years of data. So this has been published in Nature Journal, and students can go through this. That is our JRC Global Surface Water Episode. Thank you.
Have any query? Please feel to ask directly or the uh, chat box or the chat box.
Hi, am I audible?
Yeah.
Yeah, Dr. Pradhan, I just wanted to ask one thing. So what we discussed so far, I think it's based upon the dams that we are putting on rivers.
Yes.
And I just wanted to extend it and see that if we see it in the context of river connectivity, so
Yes.
will it be possible to then predict the impact, environmental impact, or how a braided river or an unbraided river will behave if we are connecting two rivers through a channel? Will it be possible to predict it through this study?
So prediction means you are talking about this morphological prediction, sir.
Right,
Or
right. Morphological.
yes, sir. So currently, what we have the river process-based model on the morphological models are there. They can predict a certain degree towards how the morphology change will be there. But this study was, sir, initially conducted for our European research. For our Indian research, what the morphological prediction is still in this in the preliminary stages. So what we have seen that if we can categorize our channel forming discharge or the discharge which is controlling our river to a certain degree for a shorter time period, that is 5 to 10 years, we can predict the morphology change. But currently also we have this indication of the climate change impact, because from the climate change, if the discharge is changing, upstream flow is changing, that also contributes to the changes in the channel forming. So we have certain degree of empirical equation as well as mathematical models are there. They can predict the channel change to a certain shorter time period. For the longer duration, morphological prediction is still it is very difficult because many parameters are there and many interactions are happening.
So for the current projects, then how they are factoring these things? I mean, just little curious to know. So when since these
Current
projects are
projects, the future-based morphological prediction is still not there, sir. Currently, what they are looking like last next 1 to 2 years, how the morphology change will happen based on the remote sensing or the field-based investigation. So what they look into this, sir, like in case of the Brahmani River, when they develop this uh, inland waterway project, the morphology change was happening because the water depth inside the river was changing. Water depth was decreasing. So they said that you form one numerical model, so that numerical model can tell us if we place different location, different wear and barrages, how this morphological pattern will be there and what the depth scenario will be there. So currently they are looking at what is the present condition of the morphology, and from the past how it is changed to the present part. But in the future it is still in the very much preliminary stages of future prediction of the morphology.
understood, understood. So there is a research gap then.
The way we can do, sir, like through climate change study, we can generate the future discharge scenario. That future discharge scenario can be fit into any kind of numerical model, and we can certain degree we can predict what is the future morphological behavior will be there. So through numerically we can do it, sir. Like climate change to the future discharge to the process-based understanding of the morphologic model. Like currently we have DEL 3D is there and CCSE 2D sediment transport model. They can predict the morphology change behavior based on the future discharge.
Got it.
Uh, have any query, please? I think no, sir.
Okay.
Uh, Thank you so much, sir.
Thank
Uh,
you.
Dr. Pradhan, sir, your insightful and research-rich session. Your lecture today has greatly enhanced our understanding of heterogeneity in fluid system and impacts how river dynamics vary significantly based on geomorphic, hydrological, and anthropogenic influence. The discussion on the location probability index provided a valuable analytical tool for interpreting spatial variability within a river system. Your emphasis on the importance of field-based investigation reminded us the real-world river behavior cannot be fully captured through model alone. Ground truthing and field survey remains indispensable in fluidal research and river management. Overall, your session offered a deep and data-driven perspective on the river recovery, geomorphic indicators, and complex behavior of large impetus river, a topic both academically enriching and practically relevant. We truly appreciate your time, expertise, and commitment to advancing the civil engineering and water resource engineering. Thank you, sir.
Thank you. Thank you, everyone.
Uh, oh, Now, we kindly request to all the participants, please stay connected with us. We now moving on to our next expert session at 3 o'clock. Please stay here. Next session will be start at 3 o'clock.
Can I? I'm sharing my screen now.
Okay. Now, moving
Yes.
ahead.
Can you see my
Yes, sir.
presentation?
Visual, sir.
Okay.
Okay, just a second, sir. Mm, it's my privilege to introduce our distinguished speaker, Dr. Pratik Gupta, Associate Professor in the Department of Civil Engineering at the Indian Institute of Technology, Delhi. The completed his bachelor in civil engineering from IIT Madras and earned his PhD from Noaga University, Japan, specializing in structural engineering. Dr.
Yes.
Gupta's primary research interests lie in the areas of consecutive modeling, finite elements analysis, concrete mechanics, and advanced construction materials. His works focus on the development of innovative and sustainable materials, including self-compacting concrete, fiber-reinforced composite, and the geopolymer concrete. He has also explored the uses of industrial and construction waste, such as marble and granite waste, for enriching the performance of concrete. A strong advocate of sustainable infrastructure, Dr. Gupta sir contributed significantly to the development of low carbon construction technologies, bamboo based structural system, and eco efficient cementitious material. He has published numerous research articles in the reputed international journal and book chapter, and has actively participated in conference, workshop, and collaborative research. His academic leadership extend supervising doctoral and postdoctorate students, contributing to curriculum development and engaging the interdisciplinary projects. He is also an active reviewer for various international journals in the structural and materials engineering. We are excited to gain insight from his vast academic and research experience in now session. Welcome you, sir. Please, sir.
Uh, Good afternoon, everyone. Shall I start?
Yes, sir. Please, sir.
Can you hear me?
Yes, sir. Yeah.
Okay. Let me, before the presentation, introduce myself a little extra. Born in Assam, then I did my schooling in Ramakrishna Mission Vidyapit Devghar, and my 11th, 12th was in Calcutta. And then I was lucky to got enter into IIT in my first attempt with 326 J rank, and I graduated from IIT. Uh, I graduated from IIT Madras, and I was lucky that 12 years I was in Japan, where I had got fantastic exposure. That's a in just to explain that Japan is a very engineering oriented country, not a MBA oriented country. So
Yes,
it
sir.
has it had, at least in past, huge respect for engineering, and I was lucky that I got a time education in a time when I was introduced the right technologies which I am now using here. And since 2003, I'm working on concrete technology. Though I have worked a lot of consultancies in bridges and retrofitting also, but my main research is concrete technology. I have extensively, as introduced, worked on cement, fly ash, marble powder, granite powder, worked on durability aspects also. But today I would like to touch upon the sensitivity of the knowledge of concrete, which is very important, and I think you will realize what I'm talking when I'm making the presentation. So the topic of my presentation is, let me share the this thing again. Okay, can you see it?
Yes, sir.
Okay. The topic of my presentation is concrete, the least understood, most important construction material. We have heard of a lot of failures of bridges recently in Bihar and various other places. Obviously, design defects are one of the reason, but I think the problem of concrete technology played a very important role in failure of many of the bridges. And I am sad to say that I was born in a construction family, and there also I saw with my father's construction firm. I don't blame him, because that time even the plasticizers were not there, and the knowledge of concrete was very sad. I came back to New Delhi in 2003, where in Japan I got extensive experience of using plasticizers and the modern concrete technology. But 2003, when I joined IIT Delhi, Professor Sinha, who is a very reputed engineer, was teaching, and he was teaching concrete without plasticizer. I was surprised, and today I will be surprised if any scientific experiment construction goes on without plasticizer. However, the truth is slightly different. Most of the constructions in the unorganized sectors are going through an epidemic where plasticides are not being used, where PPC is being used, and the concrete quality is really sad. And I am looking for a solution, and I don't find any solution because people are not ready to cooperate. Because obviously, you don't decrease the price without implementing technology. You can see different type of failures that happens in the concrete. Let us understand the root cause of the problem. Our country has a code called 10262, which is on concrete mix design. There are 6 7 examples in the end given in the mix design 10262. Let us look into the annexure A. It is about a M40 design using PPC. It does not it does not provide a graph specifically for PPC. With target strength of 48.25, that is M40, W by C is taken as 0.36, and from table 4, water was taken a 186 for 50 mm slump. You have to remember this 50 mm slump with 186 is the slump expected from zero plasticizer. And if you want to increase it, 70 every 25 mm, 3% water has to be added. And so if I take 75 mm as the example, or 125 mm for pumpable concrete, the water will be 191 or 202. And from that, uh, the code explains that 23% reduction of water due to plasticizer. Where does this 23% comes is not explained. Should it be 23? Why not 15? Why not 10? Is not explained. And it is left because plasticizer cost can be as low as 30 rupees to 150 rupees. Obviously, the water reduction capacity is not same for all plasticizers, but the code does not explain that. It knows the answers, so that is why it takes a 147.52. As per our data, this will provide marginally lower strength than 48, something of the order of 47 MPa for PPC. This mixed design will come, and let us assume this is correct. Followed by this, it gives a water correction example. Water correction actually should be is one of the very important thing in concrete about the quality of concrete. In a mixed design, typically sand will be around 800 kg. So if there is an extra 3% of water, it will become 24 kg, which will destroy the WYC in a very bad way. So water correction should be a construction stage work activity, not a mixed design stage activity. But this annexure A takes an example of dry sand and shows the water correction. And I have seen so many mixed sand coming from small laboratories which follows the same method and says dry sand, this is the methodology. As if the contractor have to use the dry sand without correction, so they don't bother that correction should be done. But the actual sand need not be dry, it actually can be wet also partially. Basically, you can see we did a lot of experiments with the WIC curve. The 43 and 53 grades is the top curve, and the PPC is the bottom curve. And you can see that 43-53 graphs are almost similar to each other, whereas PPC is slightly almost 4 to 5 MPa lower than the normal graphs. So in the second example, annexure B, same example is given. Again, M40 example is given. And here it is saying fly ash along with fly ash.
Sir, I think
Obviously,
slide is not moving, sir.
Yes.
Slide is not moving, sir.
Why it is not moving?
Please,
Hello?
yes, sir. Please go to slide mode, sir.
So now are you able to see annexure B?
No, sir.
You're not seeing slide number 6?
No. Now
What
is
about now?
yes. Okay, sir.
Okay, let's follow this mode. Uh, so in the annexure B, it is a 40 MPa design with OPC and fly ash. With OPC and fly ash with a target strength of same 48.25, and table 4 same thing as you have seen before, 186 and 50 mm slump and increase of 75 mm because I want to increase this for let us it gives us 120 mm is the target slump, so it is
So the
basically
slides moved
defining.
away completely.
Yes,
Slides moved away completely now. We don't see the slides.
I've not changed the
No, actually, slideshow is not visible, sir. Slides is not visible.
slide is not visible.
Yeah. I think I removed the here.
What about now?
Yeah.
Okay. So in this example, the slump was 120 mm.
Kindly, can you give some
Yes.
second slide once, sir? Because we have not seen the slides.
I'm not able to hear you. Hello?
I think I wrongly mute, sir. Mute.
Have I muted?
No, no, okay, sir. Continue, please, sir.
Okay. Shall I continue?
Yeah.
Okay. So basically, it is an example where 120 mm slump is assumed. By that, the water comes out to be 201. And again, same 23% has been taken. The water comes out to be 155. And based on WIC 0.36, the cement was calculated to be 431. And to calculate the fly ash, it arbitrarily increases this value by 10%. So, and then assumes 30% of it is fly ash. So the fly ash volume becomes 30% of 1.1 times into 431, which becomes 142 kg per cubic meter. And cement accordingly will be 332 kg per cubic meter. You can see the table in the side. The first example is what this thing. According to my calculation, the strength of this will not come 48.4525. It will come around 40 MPa, and this is absolutely a wrong design. And this 10%, I'm giving you the example of 0%, 15%, 25%, 45%. Maybe I will help you by increasing the size of this graph so that you can see it better. Can you see the table now little bigger? Hello?
Yes, yes, sir. Yes, sir.
Okay. Now you can see the correct examples of 0%, 15%, 25%, 35%, 40%. And you can see as I increase the fly ash percentage, the powder content is continuously increasing. So this 10% which they have assumed is not a standard rule. It actually should depend on the fly ash percentage. And you can see that all these five mixed giants will have same strength, and the cement quantity is gradually growing down. And this type of example is not possible by 10262. And imagine a country like us, it is still not able to provide a mixed design method to our country, and they are all so knowledgeable people, and still they are not able to give us a design where people can follow the code and provide the design. It is actually a very sad state of the world. From this, basically, if you, I'll go back a little more slides here. This graph which I had shown, that is OPC 43. This is the graph. You can see as the mixed design proceeds, the water can be taken, when the WIC is very low, we can take a low quantity of water. But when we want to increase the WIC to low strength concrete, we have to increase the water, because in control concrete, the powder quantity is not sufficient. However, when we do fly ash concrete, the powder becomes sufficient, and we can have the lower amount of water, and we can have good concrete. So fly ash design, as we have seen in the next slide, we can achieve very high powder content. And when the powder content is good, the concrete is like a paste, and it is very cohesive. And the concrete surface that comes out is very, very beautiful. There is no segregation inside the surface. Just some time back, Rachi, one construction, took up fly ash for the first time, and after the construction, they came back and told me, "Sir, the surface is so beautiful that we can't imagine with control concrete." The reason is that because of the extreme this thing. If we use fly ash, the durability is enhanced. It becomes economic. Again, going back to the slide, the most economic thing is the cement. You can see that it starts with 437 for control concrete, and the final 35% at least you take 370 kg. So you can assume almost 67 kg of cement has been saved. So it's a huge saving in cost that we find out. And we also get durable concrete, cost benefit, and it also utilizes byproduct of the industry. So we are having an environmental this thing. The control of segregation is not there, bleeding is not there, and the mix is very good, and the finish is also very good. So it is actually sad that in our country, in the unorganized sector, fly ash is not available. They are forced to use PPC, which is not a good choice. Till we understand our rights, that we also should be able to get the OPC plus fly ash mix, we will always be misutilized by our cement industry. PPC is not good in any sense because neither in durability, neither in powder. So mix design that I follow is where we have a concept called efficiency factor, where efficiency factor is defined by the equivalent cement of the material being used. So if we are using fly ash, so it is the efficiency factor that we take, and the K factor is given in this graph where it is which is decreasing, and as a result it is actually less efficient material but very good for concrete because we can achieve that at a low cost. The side graph which you can see, I will just make it a little big for your visibility. This is the fly ash limit. Till around zero point 0.5 we can cast control concrete. After that it is impossible to cast control concrete, so we must incorporate some sense of powder, whether its powder is from fly ash or model powder. But without sufficient powder we cannot make good workable concrete. So you can see there is an upper limit and a lower limit and the optimum limit. The three was done by Kuito, and the high strength to normal strength extensive work was done by Kumar, and the low strength part was done by Mira. That is how this graph was developed, and based on this, we do our mix design, and this is the process basically. We choose based first. We take the grade of concrete. In grade of concrete, suppose M40, the design strength target strength is 48.25. In our method we add another 3 ampere to it and make the design method. Why we do it? Because every time we do casting there is an error in the casting process also. So to take care of that we add another 3 ampere to it. So M40 we design generally for 51 52 ampere. From that we find out the K factor, WYC required, and we based on WYC we find out the fly ash percentage, and based on fly ash percentage we'll get the K factor and we can do the design. In the design, let us see an example design. Again I will maybe magnify it a little bit. You can see now the first example is that of M10 concrete with 50 minimum 55% to 85%. You can see in 55% the powder is barely 281. It is not sufficient. In the 65% we can get the 336, which is a good amount, and 554 will be fabulous concrete. And this is M20, this is M10 concrete. Now you can see the cement consumption, which is 126 in the first stage, goes down to 83 kilo. So M10 concrete we can do even with 83 kg. In the second case, we have taken lower fly ash percentage, 0 to 45%, and we have added marble powder to it and still got very good concrete. And the third example, we have added foam to it, and that's beyond the scope of the this thing. Basically, in WYC for foam concrete, we've added foam to the numerator, and it gives us a fantastic mix and procedure. In contrast to this, if we go for the next design, that is the M40 concrete. So in M40 concrete, you can, this is not M40, basically it's 47. So that implies it should be around M35 concrete. So this is not correct M40, this is 35 concrete. So in that sense, you can see 0 to 35% fly ash we first take, and we can decrease cement content. Then my same design philosophy says that though we have assumed 155, The contractor, as in the trial stage, we can try out 150, 150, 160 and check which one is good concrete and which one is bad concrete. In the third set, marble powder is introduced. You can see that control concrete is taken and 0% fly ash, and we added marble powder to it. And in the third case, we have taken 15% fly ash, where we get a significant saving. You can see that from 388 to 399, almost 49 kg of cement has been saved by this method, and we are able to utilize the marble waste also. Now, the most important thing that I always talk in the class is the water correction. For water correction, we always have to find out what is the saturated surface dry, moisture content, and the water absorption and the specific gravity. We follow the American standard using the cone and this method. And after finding out, we have to do the water correction. The example I am showing is the effect of water correction that you can see. So the first green one is the mixed design with water 175, cement 350. So this is a control concrete, and seven sand is 713, 1020, 465, 698, and W by C is zero point 0.5. So zero point 0.5 means expected around 30 MPa. We'll see that. Suppose there is an extra, suppose assume the moisture content is 3% and the specific gravity SSD moisture content is 1%. So that implies we have 2% extra water. So 2% of 730 is around 14 kg. Our W by C zero point 0.5 will become 0.54. And if there is 5% extra moisture, which will become 4%, our W by C will become 0.58. You can see that the black mark is the line and the red mark are the other 2 points. So you can see the strength has decreased almost 5 MPa, which is very, very important. But if you do the water correction properly, you can see actually all 3 points are within the same line only. So water correction is the one single most important parameter for quality control of concrete. I have seen so many examples in which people are not knowing how to do water correction, and we sometimes call their technicians and teach them how to do water correction in IIT Delhi. And I will be proud to say that I am one of the highest consulted person in the case of mixed design. With that, my presentation is over. I would like to take question answer from you, and once you ask questions, I can talk more on other things also. I can show you many other things.
Have any query, please ask to directly or in the chat box.
Please see the questions and tell me. I will answer them.
Please ask the question.
Yes. If you don't have question, then I can proceed to present more things and talk to you about other things also.
No, I think, sir. I think no, sir. Yeah. Please, Rajesh.
So I was asking if this 10262 will be applicable to this green cement also, which is not following the conventional method of cement preparation.
I am not understanding. what is green cement?
Sir, there are like the instead of fly ash, they are using several other raw materials for which are
Like GGBS,
correct, sir, correct.
microsilica,
Yeah,
all
yeah,
these
yeah.
things you are talking about.
Right, sir. So how will we ensure that their strength is
10262 includes GGBS also.
okay, sir? Okay,
10262 includes microsilica also. M70 there is an example which includes microsilica also. But what I want to say is that the 1062 is very, very undeveloped code, and it is very sad that our country is not able to develop a good code which can help us to do the mix design.
so what exactly is the challenge, sir? I mean,
Huh?
so what exactly is the challenge in developing a code? Because that framework will be helpful in designing, considering that our country is having so much of infrastructure failure. So where lies the challenge in? Is it a policy-related challenge or is it a technical challenge?
I think first thing is that people have too much pride and they don't want to change the code. Like for example, I'll give you a small example. In the cement manufacture, in the cement quantification, the WIC after consistency is around zero point 0.4, and in zero point 0.4 WIC concrete, the expected strength is 40 MPa, but they say it is 66 MPa. How they achieve it? By using standard sand, which is dry, and they allow the standard sand to absorb water, and a modified WIC is achieved, and thereby they are creating a monopoly of the standard sand. Because if you take some other sand, there will be some other strength, and our country is not ready to learn. Our codal departments are not ready to learn even the modern sciences, and it is completely controlled by the industry, mainly by the cement industry, which have their own agenda in selling PPC rather than cement plus fly ash. They don't want to allow cement plus fly ash to be sold to the common people. So I really want to actually start a business in which I procure the cement and fly ash and sell to the normal people. Actually, I'm planning to start a business on those lines. So that's the first thing. Second thing, the knowledge of cement mix design. People always become civil engineers. People become structural engineers, but the incentive of becoming a concrete engineer is very less, and they think that is not a very respectable job, because in structural engineer you do a lot of modeling, you do engineering. It looks like engineering, but a concrete technology does not look like engineering. It looks like a layman's job, but actually it's a very, very high tech job, and it is very sad that our country does not have a good system for concrete technology. In fact,
Understood.
except IIT Madras, IIT Delhi, and few other colleges, till recently there were no concrete technology course in any of the colleges also.
Got it, sir.
Thank you, Rajesh.
So if you allow me, I can extend my presentations a little bit more, maybe another 10 minutes if you allow me.
Yes, sir. Please, sir.
I will not use slides. I will extempore say. Basically, in a concrete, the most important thing is to have lot of powder inside the concrete. That powder has to be added separately. How to use AI technology in civil engineering? Sorry, in concrete, till you have a truthful data, AI cannot be used. AI can only be used where you have data where the truthful data is available to you. But in civil department, you will not find truthful data in real any construction. So till the millions and millions of data, truthful data is available, AI technologies will be completely failed, because AI does not recognize what is called false data and what is called true data. Till you feed the AI with a truthful data, no AI can work. So first of all, AI is complete failure in at least in this field. Okay, so I'm coming back to the concrete technology a little bit presentation. A concrete becomes good when there is sufficient amount of powder, and the powder, if it comes from cement, it has a lot of negative effect and also a high cost to it. So we require low cost material. Microsilica is a high cost material. GGBS is a high cost material. Grinded fly ash are high cost material. Fly ash is the only material which is low cost. Along with marble powder, granite powder, or stone dust powder, can also be considered as zero cost material. So when we make a concrete, if we put sufficient amount of powder, it actually becomes a good concrete. But what if the powder is present along with the sand? Then it becomes a bad powder. Why it becomes a bad powder? Because that powder masks the sand and does not allow the sand to form bond with the matrix. So actually, we need to separate the fine powder from the sand and mix it with concrete. Then it becomes a very good. I have been using marble powder, granite powder, and recently stone dust powder. They're so beautiful material, and we are underutilizing them. And we are not utilizing them because IS code does not explicitly allow it. That is why it is not being used by any contractor. I have finished my research almost 10 to 15 years back, but still I am not finding a single contractor ready to use my design with marble and granite powder. But I hope in future people will actually use this marble and granite powder. And one beautiful thing in marble and granite powder is that they come almost in similar powder size. So we don't have any problem in the quality of this material. It is not like the stones where the particles are flaky or something else. They are all of similar small size. So, in if you want to have good concrete technology, your powder must be high. Your plasticizer must be best of the quality. Should be high cost, and once you do this, you can also have a high durability by using microsilica or fly ash. But many times durability is not necessarily an important criteria. In that case, we can use marble powder, granite powder, or any other stone dust also. So when you design a concrete, you have to have a very good, strong understanding of the powder. And as you can see, when I design the concrete with high volume fly ash, the powder content which is around 500, 550, and the concrete actually uh, is a very nice cohesive matrix. And till now, my experience is that fly ash is one of the most beautiful material. But if you want to design, say, M80 concrete, M70 concrete, there the powder is already very high. There we are looking for highly efficient powder, and we are doing research. By grinding the fly ash, the efficiency factor can be made 3 times, 4 times better. And we are thinking that maybe we can decrease the cement content by using grinded fly ash. And the grinded fly ash cost need not be high, it can be low as 3 to 4 rupees per kg. Thank you very much.
Okay, thank you, sir. Thank you so much, sir, Dr. Gupta, sir, for your highly informative and thought-provoking session. Your lecture shed light on paradox of that while concrete is the most widely used construction material, it remains one of the least understood. Even by many professionals in the field, the discussion on bridge failure due to concrete deterioration was particularly eye-opening, reminding us how structural integrity is often compromised not by design flaws but by improper understanding and execution of concrete works. The explanation of honeycombing cause and
One One last thing, I have a YouTube channel, Shupratik Trust. You can see the experiments in that. I have actually uploaded various experiments in that, and how to do water correction, how to measure specific gravity. All these things are there in my YouTube channel. You can check this. And if you want to have any live experiment class, I can do a demonstration class live also.
thank you, sir.
So if the students are interested, I can show them what is water correction, and those are important things. And I can show them control concrete, fly ash concrete. All those things are there in the Shupratik Trust YouTube channel. If you want direct, I can also arrange for that also.
Also share the participants group, sir. Thank you, sir. We sincerely thank you for your time and invaluable insights, sir. Thank you, sir.
So I can take a leave.
Yeah, thank you, sir.
Okay. Thank you very much.
Okay. Now it's for a feedback session, and after the feedback Just a second, I share the link feedback. Also, the validity session. Have any feedback for us? Please suggest us. May I request to Rizwan Khan, sir, please give us some feedback for us for better. Sanil Kumar, please.
Hello, I am audible.
Yeah, audible, sir. Please,
Okay.
sir.
Good afternoon, everyone. I would like to thank to the Department of Civil Engineering, Rajshree Engineering College, Bareilly, for organized wonderful 5-day FDP program. All the sessions were informative, well structured, and covered crucial engineering areas like urban infrastructures mapping, structural health monitoring, environmental engineering, etc. And it was a great learning experience for me. And I thanks to the convener of this program, Professor Anup Verma, Head of Department Civil Engineering of RIMT Bareilly. Thanks
Thank you. Thank you,
to
sir.
Dr. Anup Verma.
Thank you, sir. Have any, please? Okay. After 5 minutes, the validity session, and I share the feedback link. The chat box. Please complete the feedback. Please now check the link. Now open the link. Please check. Okay. Now, uh,
Hello.
yes, I warmly welcome to Dr. Pankaj Kumar Sharma, sir. Sir is our director. So, sir, please give a motivation words for us.
Uh, Thank you, Professor Anuj. Very good evening, everyone. It is indeed a moment of pride and satisfaction as we come to the conclusion of the 5-day faculty development program on recent advancement in civil engineering organized by the Department of Civil Engineering in collaboration with the Institution of Engineers India Very Local Center, Bareilly, UP. Over the 5 years, 5 days, we have had a privilege of listening to eminent speakers, gaining insight into cutting-edge research, technological innovations, and transformative practices in the field of engineering. I am confident that knowledge shared during the faculty development program will inspire new ideas, improve teaching methodologies, and strengthen our academic and research pursuits. I extend my heartfelt thanks to all the distinguished speakers, Professor Dr. Akhilesh Kumar Maurya from IIT Guwahati, Dr. Chandar MC from NIT, Dr. Ketan Kumar Nandiji from SR University Warangal, Dr. Nidhi M NIT Pondicherry, Dr. R.D. Gar Professor from IIT Roorkee, Dr. Jacqueline Jack Niling from NIT, Dr. Chandan Pradhan, NIT Karnataka, and Dr. Suprit Gupta from IIT Delhi. For their valuable contribution, I also appreciate the efforts of the organizing team led by the Professor Anuj Verma, head of the Civil Engineering Department, Rajshree Institute of Management Technology, for the seamless execution of the program. To all the participants, Your dedications and active engagement made this event a true success. I encourage you to take forward what you have learned and implement it meaningfully in your institutions. Let's continue to collaboration, innovation, and strive for excellence in engineering, education, and research. Thank you all, and the best wishes for future endeavors. Thank you.
Thank you, sir. Thank you, sir. Now the completing 5 days faculty program is indeed a moment of pride and satisfaction as we come on the conclusion of 5 days faculty development program on recent advancement in civil engineering organized by the Department of Civil Engineering in collaboration with the Institution of Engineers India, Bari Local Center, Bari. On the behalf of organizing institute, I extend my heartfelt gratitude to all our distinguished speaker who's deliver the lecture on such as Dr. Akhilesh Kumar Maurya sir. He delivered smart, sustainable, and immersive AR, VR, and autonomous vehicle technology in the next gen civil engineering. Sir is from IIT Guwahati, and next one speaker at, in first day, the Dr. Chandan MC. Sir is guided us related to urban infrastructure mapping, geoinformatic approaches. Sir is from NIT Karnataka. After that, the Dr. Ketan Kumar Nandi, he is described in the application of cloud computing in river corridor management. Sir is from SR University, Varangal. After that, the Dr. Nidhi M. Ma'am is discussing about the structural health monitoring of slender masonry heritage structure. Ma'am is from also, NIT Pondicherry. After that, the Dr. R.D. Garg sir. Sir is guided us related to the latest in trends in geospatial engineering. Sir is also from IIT Roorkee. After that, the Dr. Jacqueline J.K. Neeling sir is guided as related to the towards in situ remediation of inorganic contamination in mixed toxic groundwater possibilities and pathway. Sir is from NIT Karnataka. Today, Dr. Chandan Pradhan has described and guided us and discussion about recent advance in river recovery and advanced flow survey techniques. Sir is also from NIT Karnataka. And the last session is Dr. Supratik Gupta. Sir is from IIT Delhi and also guided in the form of concrete, the least understood, most important construction material. Your valuable insights and engaging session have enriched this program immensely. I would also like to place of my record my sincere appreciation for the effort of the organizing team by lead by me, head of department civil engineering. Finally, my thanks go to all the participants for their active involvement throughout the question enthusiasm, which made this FDP is a true collaborative learning experience. Thank you to all. Thank you. I have also sent the feedback link in the chat box. Thank you.